Good day. Today we're going to discuss the inverses, algebraic properties of matrices. In this discussion, we will talk about some of the algebraic properties of matrix operations. We will see that many of the basic rules of the arithmetic of real numbers holds for matrices. But we will also see that some do not. So let's have properties of matrix addition and scalar multiplication. So theorem 1.4.1. So properties of matrix arithmetic. Assuming that all sizes of the matrices are such that the indicated operations can be performed, the following matrices or following rules for matrix arithmetic are valid. So we have the commutative law for addition, associative law for addition, you have associative law for multiplication, left distributive law, right distributive law. Then you have that one, you have A times the quantity B minus C is equal to AB minus BC. And you have the quantity B minus C times A is equal to um, BA minus CA. And you have the scalar A times the quantity B plus C is equal to AB plus AC, and so on. So we have properties of matrix multiplication. Now, um, what we call this one? Do not let the theorem 1.4.1 lull or soothe you in believing that all laws of real arithmetic carry over to matrix arithmetic. For example, you know that in real numbers or real arithmetic, it is always true that uh, you have, let's say, uh, you have AB, which is equal to BA, okay, which is called the commutative law for multiplication. In matrix, okay, matrix arithmetic, the equality of matrix AB, and matrix BA can fail for three possible reasons. Number one, if AB may be defined and BA may not. For example, you have 2 by 3. If a matrix A is, what you call it, if matrix A is uh, 2 by 3 and matrix B is 3 by 4. And then the second one, AB and BA may both be defined, but they may have different sizes. For example, if matrix A is 2 by 3 and matrix B is 3 by 2. And then you have AB and BA may both be defined and have the same size, but the two matrices may be different. Okay, so let's have first. Let's have an example. Uh, so if ever, for example, if you have, let's say, uh, you have matrix A is equal to, let's say, negative 1, 2, 0, 3, and then our matrix B would be uh, 1, 3, 2, 0. Then, if we are going to have the AB, uh, Then you have here, this is -1. Here you have 11. Here you have -2. And here you have 4. Then if you have matrix EA, okay, equals, here you have, in this case, you have BA. So this one to the other one. You have 3. Here is -3. Here is 6. And you have 0. So as you can see, you have AB is not equal to BA. Okay, so you have 0 matrices. Okay, so 0 matrices. A matrix whose entries are all zeros is called zero matrix. So that's what we are going to have that definition. We will denote a zero matrix by 0 unless it is important to specify its size, in which case we will denote um, the m by n. You have m by n. Okay, if that would be a zero matrix, then you could have 0 sub m by n. Okay, um, it should be evident that if A, matrix A and 0 are matrices with the same size, then we could have A plus 0 is equal to 0 plus A, which is equal to A. So 0 plays the same role in this matrix equation by the number 0 placed in the numerical equation. Remember, if any number added by 0 is equal to itself. So we have the following theorem. Okay, list the basic properties of zero matrices. Since the results should be a self-evident, we are going to omit the formal proofs. So you have theorem 1.4.2, the properties of zero matrices. If C is a scalar and if the sizes of the matrices are such that the operations can be performed, then you have the uh, a plus 0 is equal to 0 plus a, which is equal to a minus 0 is equal to a minus a is equal to a plus the quantity in the negative a, which is equal to 0, then 0 times a is equal to 0, and if CA is equal to 0, then C is equal to 0 or A is equal to 0. Okay, so let's have the identity matrices. A square matrix with ones on the main diagonal and zeros elsewhere is called identity matrix. So you have there the examples. So this would be the identity matrices. Okay. The an identity matrix is denoted by a letter I. Okay, italic I. If it is important to emphasize the size, we will write the uh, I sub n for the identity matrix. Okay, to explain the role of identity matrices in the matrix arithmetic, let us consider the effect of multiplying a general 2 by 3 matrix A on each side by an identity matrix, multiplying on the right by the 3 by 3 identity matrix K. So that one. So as you can see that if we are going to multiply the uh, 3 by 2, the general 3 by 2, by the identity 3 by 3, the outcome would be the same as matrix A. Okay. And multiplying on the left by the 2 by 2 identity matrix, okay, if you have that one, again, we could have the uh, outcome of the A. Okay, so the same results holds in general. That is, if A is any m by n matrix, then you could have we have this notion that you have A matrix A times the identity matrix uh, by identity matrix n, which is equal to A, and you could have the identity matrix M by A, which is equal to A. Therefore, the identity matrices plays the same role in this matrix equation that the number one plays in the numerical equation. You have A times I is equal to 1 times A, which is equal to A. So that's the identity matrix, identity number, identity property. Okay. Identity matrices arise naturally in studying reduced row echelon form of a square matrix. So you have theorem 1.4.3. If R is the reduced row echelon form of an n by n matrix A, then either R has a row of zeros or R is identity matrix I sub n. Okay. So inverse of a matrix. In real arithmetic every non-zero number A has a reciprocal A raised to negative 1, which is equal to 1 over A, with the property that A times the inverse of A is equal to the inverse of A times A, which is equal to 1. The number A raised to negative 1 is sometimes called the multiplicative inverse of A. In our next discussion, uh, our objective is to develop an analog of this result for matrix arithmetic. For this purpose, we make the following definition. So you have definition: if A is a square matrix and if a matrix B of the same matrix can be found such that AB is equal to BA, which is equal to the identity, then A is said to be the invertible or the non-singular, and B is called inverse of A. If no such matrix B can be found, then A is said to be singular. Okay, let's have an example. So let you have matrix A, 2, negative 1, negative 5, 3, and B, 3, 1, 5, 2. Now, if we are going to multiply this one, okay, if we are going to multiply, you have, let's say, AB, then you have 2 times 3 minus 5 times 1, which is equal to 1. Here is 0, then 0, and 1. Okay, so that's identity. Okay, identity. Then, if you have BA, Then you have 3 times 2, 3 times 2 plus 5 times negative 1, which is equal to 1. Then, so on 0, you have 0 and 1, which is equal to identity. Okay, in other words, A and B are invertible and each is an inverse of the other. Okay, so properties of inverses. Okay, it is reasonable to ask whether the invertible matrix can have more than one inverse. And of course, this theorem, okay, shows that the answer is no. An invertible matrix has exactly one inverse. As you can see here in the theorem 1.4.4, if A and C are both inverses of matrix A, then B is equal to C. Okay. Now let's have the next theorem, 1.4.5. The matrix A, which has entries of A, B, C, D, is invertible if and only if you have A times D minus B times C is not equal to 0, in which the case the inverse is given by the formula. You have A raised to negative 1 is equal to 1 over A D minus BC times that one. The C minus negative B negative C A. Okay. So technically, the A D minus BC is the what we call as the determinants. If you can still remember in your previous discussions when you were still in your baccalaureate degree. Okay. Example, in each part, determine whether the matrix is invertible. If so, find its inverse. Okay, so let's have the solution. Now take note that for the number 1, okay, solution for number 1, okay, you have, uh, in this case, we have to determine first the determinant of A, which is equal to, in this case, 6 times 2 minus 1 rather, 1 times 5, which is equal to 7. Okay, since the determinant is not 0, therefore A is invertible. And the inverse would be, so you have the inverse would be 1 over 7 times, you have um, 2, negative 1, you have negative 5, 6, which is equal to, you have 2, 7, negative 5 over 7, negative 1 over 7, and 6 over 7. Okay. Now, for number 2, as you can see, for number 2, you have the determinant of A is equal to negative 1 times negative 6 minus 2 times 3, which is equal to 0. So in other words, the second matrix is not invertible since the determinant of A is equal to 0. Okay, so let's have the theorem 1.4.6. If A and B are invertible matrices with the same size, then AB is invertible, and the inverse of AB is equal to the inverse of B times the inverse of A. Okay. For example, you have consider the matrices uh, A 1, 1, 2, 3 and B 3, 2, 2, 2. Okay. So now, if we are going to solve for AB, okay, we could have you have here 7, 9. Here is 6, and here is 8. Then, if we are going to get the AB inverse, so you have uh, 7 times 8 minus 6 times 9. Okay. Okay. So you have here uh, 1 over, uh, you have 56 minus 54 is equal to 2 times 7, 9, 6, 8. No, I'm wrong. It should be 8. Then you have negative 9. Then you have here negative 6. And you have 7, which is equal to, as you can see, uh, you have 4, negative 9 over 2, you have negative 3, and 7 over 2. Okay, so if you have the inverse of negative 1, okay, um, you have here, um, following the process, okay, 3, 1, a negative 1 other, and then 2, 1, then the inverse of negative b would be um, uh, huh, 1, negative 1, negative 1, 3 halves. Then you have the b, okay, the inverse of b and inverse of a is of course the product of, you have this one times this one, which is equal to 4 negative 9 halves negative 3 7 halves. So in other words, as you can see, that you have the inverse of AB is equal to the inverse of B times the inverse of A. Okay. So power of a matrix. If A is a square matrix, then we define the non-negative integers powers of A to be that one. A raised to 0 is equal to the inverse, and A raised to n is equal to A times A times A up to A, and factors. And if the matrix A is invertible, then we defined the negative integer powers of a to be that one. So a raised to negative n, which is equal to the inverse of a to the power of n. And that would be equal to a raised to the inverse of a times the inverse of a up to a raised uh, a, a inverse inverse of a and factors. Because this definition parallel those of the real numbers, the usual law of non-negative exponents holds. Okay. For example, you have a raised to r, which is a raised to r times a raised to s, which is equal to a raised to r plus s. And the a raised to r raised to s is equal to a raised to r times s. Okay. If the product of matrices is singular, then at least one of the factors must be singular. So let's have a theorem 1.4.7. If a is invertible and n is a non-negative integer, then the inverse of a is invertible, and a the inverse of a times you have the inverse of a is equal to a. Now, if the a raised to n is invertible, then you have the a raised to n, the inverse of a raised to n is equal to uh, a raised to negative n, which is equal to uh, the inverse of a raised to n. And then ka is invertible for any non-zero scalar k, and the inverse of ka is equal to the inverse of k times the inverse of a. Okay. For example, we have this one. So let a, you have the entries 1, 1, 2, negative 1, 1, 2, 3, and the inverse of a is 3, negative 1, negative 2, 1. Then, okay, if you have a raised to 3, then that would be equal to uh, the inverse of a raised to 3, which is equal to you have 3 times negative 1, negative 2, 1, 3, negative 1, negative 2, 1. Then you have 3, negative 1, negative 2, 1. Okay. So, which is equal to, you have 9 plus 2 is 11. Then you have negative 3 minus 1 is negative 4. Then you have um, 3 negative 6, negative 6 minus 2 is negative 8. Then you have uh, 2 plus 1 is 3 times 3, negative 1, negative 2, 1, which is equal to, you have 41, negative 15, negative 30, 11. Okay. Also, by theorem, uh, that would be that one. it is also expected uh, from the theorem, which is in the second theorem, the invertible. Okay, so this one, this one is also hold the same to a times negative 1. Okay, so let us matrix polynomials. Um, if a matrix is a square matrix, say n by n, and if the polynomial x of a sub 0 plus a sub 1 x plus a sub 2 x squared plus so on plus a sub m times x raised to m is any polynomial, then we define the matrix A, a matrix polynomial A, to be the matrix polynomial A of the a sub 0 times I plus a sub 1a plus a sub 2 a squared plus so on plus a sub m times a raised to m, where I is an identity matrix, that is, the polynomial of matrix A is obtained by substituting A for x and replacing the constant term A sub 0 by the matrix A sub 0i. An expression is called matrix polynomial in A. Okay. For example, you have the polynomial of matrix A for polynomial x is equal to x squared minus 2x minus 3, and the A is equal to negative 1, 0 to 3. Okay. For our solution, so you have the polynomial of A is equal to a squared minus 2a minus 3i, which is equal to, you have negative 1, 0 2 3 quantity squared minus 2 times, you have negative 1, 0 2 3 minus 3. Okay, identity 1 0 0 1. Okay, so you have to square this one, okay, which is equal to 1 0 4, then 9. That's 9. Minus, of course, you have 2, negative 2 0 4 6. This is 6 minus 3 0 0 3, which is equal to, in this case, you have 0. This is 0. This is 0. And of course, this is 0. So in other words, okay, the uh, polynomial, okay, in other words, the polynomial of matrix A is equal to 0. Okay. Okay, properties of transpose. So the following would be the list of the main properties of transpose. So you have a theorem for 1.4.8. If the sizes of the matrices are such that the stated operations can be performed, then you have the transpose of the transpose of A is equal to A. The transpose of AB is equal to the transpose of A plus transpose of B. The transpose of B minus A minus B is equal to transpose of A minus transpose of B. Then you have the transpose of KA is equal to the K times the transpose of A. And the transpose of AB is equal to the transpose of B times the transpose of A. Okay. So you have uh, theorem 1.4.9. Ah, by the way, let's go back here before I forget. Now, if you keep in mind that transposing a matrix interchanges its rows and columns, then you should have a little trouble visualizing the results from uh, A to D. For example, in part A, states that the obvious fact that interchanging the rows and columns twice leaves a matrix unchanged. And of course, in the part B, states that adding the two matrices and then interchanging the rows and columns produces the same results as interchanging the rows and columns before adding. In part E, it's less obvious, but for brevity, we will omit its proof as well. The results of the part can be extended to three or more factors as stated as the transpose of a product of any number of matrices is the um, product of the transposes in the reverse order. Okay, so let's have the theorem 1.4.9. If A is an invertible matrix, then the transpose of A is also invertible. And you have the inverse of the transpose of A is equal to the transpose of the inverse of A. Okay. So for example, we have this one. Consider the general 2 by 2 invertible matrix and its transpose. So that would be, okay, since A is invertible and since it's invertible, the determinant is non-zero. Okay. But the determinant of the transpose of A is also the same, okay, of the determinant of A. So the transpose of A is also invertible. So it follows with the previous theorem, okay, that you have that the trans okay, the inverse of the transpose of A is equal to, in this case, you have D over AD minus BC. Then you have negative B over AD minus BC. Then you have here negative C over AD minus BC. Then you have A over AD minus BC, which is the same matrix that results if the inverse of A is transposed. Therefore, okay, the theorem 1.4.9 is guaranteed. And that's the end of the presentation for the inverse and uh, other properties.